that's the one. That's always on.
Any questions?
Yeah, I can do the intro with that, But I'll be back when. Let's see if this will work. If the experimentalists can actually take the mic out. It's on, right? Yeah. Okay, let's start. A little late. It's really a great pleasure to introduce my dear colleague and collaborator, Shekhar Ramanathan here from Dartmouth. He's not coming from afar. And we just realized that this is our first visit in person here after COVID. But since we see each other at least twice a week on Zoom, I feel like, he's constantly present, in my life, right? Anyway, Professor Ramanathan is experimental physicist, kind of working at interface of quantum information science and condensed matter physics. So you see why we collaborate. And basically everything I learn about QS, right, from the beginning comes from him. We started, right, talking about it. And just to let you know how slow the scientific progress goes, we actually met in 2010 at IQC and started talking about projects. So 13 years later, we have papers together, right? If I do the math correctly, right? Yeah, 12 years later. There was something last year. So anyway, jokes aside, he actually has a degree, technical degree in electrical engineering from IIT, but from Bombay. Not Illinois, but the real IIT from Bombay, right? Like mine. And then MS in biomedical engineering from University of North Carolina, Chapel Hill. And he actually has also a master's degree in technology and policy. And then the doctorate degree in nuclear engineering from Massachusetts Institute of Technology. And for those of you who don't know, all the QS at MIT is actually at this Department of Nuclear Engineering, magnetic resonance, right?
It's done in many departments, but mostly in engineering.
Mostly in engineering, nuclear engineering. So your PhD officially is in nuclear engineering from MIT. And then actually following his PhD or postdoc at Harvard Medical School, Nottingham University, and then MIT, where you spend many years as a faculty research scientist, and then joined Dartmouth College in August of 2010.
Long time.
So a long time ago, and it's been there. Now he's a professor of physics and chemistry, right? So anyway, thank you, and looking forward to your talk.
Thanks, Vesnia. So thank you for the invitation, and thank you for that wonderful introduction. I'm going to give you a brand new talk today. So if I mess up, I apologize right now, but it's always good to try something new. I'm going to tell you about methodology more than an exact scientific result today. So one of the key tools we use in our studies of quantum systems is how do we control quantum systems? And so the title of my talk is how do we tame the interactions between spins? So to start with, I want to tell you about the people who did most of the work. So there's 3 undergraduates who have done a lot of the work that I'm going to describe on reinforcement learning for controlling spin systems. That's Will Kaufman, Owen Iskandari, and Matthew Goodbread. Madhu Raman is a visiting student from India who's completing a master's in the department. And then all the experimental work has been done by Ethan Williams and Linda Joseph, who are graduate students in the department. And the work has been funded through the NSF and the Moore Foundation. The reinforcement learning work has been done partly in collaboration with the group at MIT, Paolo Capillardo's group. All right, so there's a lot of hype recently about quantum computing, quantum information, quantum technologies. Quantum mechanics has been around for over 100 years. it helped shape our understanding of the world. It's driven a lot of technological innovation for our century. But now we're trying to develop the ability to control quantum phenomena coherently, so which means phase-preserving information in some ways. And these technologies are now being able to, people are envisioning applying these technologies for computing, communications, simulation, and sensing. And there's this continuing question that's being asked, is it truly better than a classical sensor or a classical computer? And those are hard questions. I'm not going to go into any of them. But they're definitely a new platform with which we can both develop technologies, but also explore physics and science. And while we're doing that, we understand more about what's behind this as well. So let's start out with our basic elementary unit, which is a qubit, a quantum bit. It can be a 0 state or a 1 state. That's typically how we think about it here. And then you've got an energy gap, delta E is h bar omega. Of course, this is why spin systems are really nice to look at, because a spin half system is a 2-level system. It can be in the spin up state or spin down state. You've got the same idea. We normally think of, for a spin at least, the interaction of the spin with the magnetic field is essentially a Zeeman interaction. And so you can write down the Hamiltonian, or the energy of the system is essentially the coupling of a magnetic moment to a static magnetic field. That's all it is. Now, one of the key features of quantum systems is that a quantum bit doesn't have to be in a 0 state or a 1 state. It can be in a superposition of states, and that coherent superposition of states. And that's one of the key defining features. So I alpha and my beta are arbitrary complex numbers, and the only restriction is that mod alpha squared plus mod beta squared equals 1. Okay. And when you do that, you can actually parameterize alpha and beta in terms of 2 angles, theta and phi, which then map onto the surface of the sphere, called the Bloch sphere. And that's what we always use to describe the state of a single quantum bit. So the 0 state lies on the North Pole, where theta is equal to 0. The 1 state lives on the South Pole, with theta is equal to pi. And of course, anything else is a superposition of the 0 state and the 1 state, and a particular superposition of those 0 states and 1 states. Okay, and so qubits are in that sense are just all you need to do is all you have to realize is that they can be in superposition states. When we're using quantum states, we have to realize that quantum states are extremely fragile. They're quantum mechanics, and if you learn Sakurai or your McIntyre or Griffiths, whichever textbook you're using, the quantum mechanics we learn is typically designed for closed quantum systems. I always start with an isolated system. But there's almost no system that's truly isolated. And so the moment you start interacting with the rest of the world, the superpositions can tend to collapse. Okay? And so this is what makes quantum states really fragile. So this is why we can think about states like this, like all spins up and all spins down. Or if you go back, it's called a cat state after Schrodinger's cat, where the cat is alive and dead simultaneously. But they're very, very hard to create because essentially any small perturbation is going to cause it to collapse. So our experimental platform that we use to study this in my lab is magnetic resonance. And so we're looking at spin half particles in a magnetic field. So what we're going to do is, again, think about what does the system look like. The energy is just the coupling of the magnetic dipole moment with the external field. I can rewrite this in terms of a Hamiltonian, which of course is just the energy of the system. And this is just the collective spin operators on all the spins, omega naught times I. So if I have a large number of spins in an ensemble system, each spin is going to be processing about the magnetic field at the same frequency, omega naught. Okay. So if I want to observe that system like that, you could ask, well, why can you actually observe the precession? It turns out that even though they're all processing at the same frequency, they all have slightly different phases. Okay. And because they have slightly different phases, as you see here, if you look at the net magnetic moment along the x or y direction, they're going to go to 0. There is a small net magnetization along the z direction, or along the direction of the field, but there's nothing in the transverse plane. So this is what a system looks like in equilibrium. There's a story of when Purcell was discovered, did the first experiments on NMR at Harvard, and it was apparently winter in Cambridge, and he put his head out into this, opened a window and put his head out, and was thinking about all of the spins precessing in the snowflakes as they were falling onto the ground. They're precessing in the Earth's magnetic field, and that's exactly what they do. All the hydrogen is precessing continuously in the hydrogen in the water is precessing in the Earth's magnetic field. So it's just this motion is always there. We just don't see it. So how do we do an experiment? So we apply a radio frequency field, and typically we're going to do it with a coil. So this is the NMR version. So it's an easy one. You have an inductor and you drive it with an AC field. And so if I have a field that's 2B1 cosine omega t, you can always rewrite an oscillating field in terms of two counter-rotating fields. Okay. So there'll be one that's rotating counterclockwise, a component that's rotating clockwise. And now if I look at my spins, they're precessing counterclockwise here at omega naught. There's a component of the radio frequency that's rotating in the same sense at omega, and one that's rotating in the opposite sense. We typically use what's called the rotating wave approximation if the RF field is really small, and you can drop the component that's rotating in the opposite sense. So I get rid of this one. That's called the rotating wave approximation. We ignore it. It usually does nothing unless it's really strong. And then and then if I move into a frame of reference moving with the RF, you actually see that the spins are precessing only at that frequency difference, right? Omega naught minus omega. So from the perspective of an observer in that frame of reference, it actually looks like you have a much weaker field because you're precessing more slowly. But I still do have now an RF, a static field now in that frame, and that's what this looks like. This is what the effective field looks like in a rotating frame. And of course, if I apply my radio frequencies on resonance, this term goes to 0. So now what was a really large magnetic field here, omega naught, of B naught here, essentially has been turned to 0 by applying a resonance field. And so my only field is now the one that I've applied, the radio frequency field. And my spins are going to start to, it's a field along X, and my spins need to start out along Z, and I'm going to start to precess about them. And that's how we rotate spins. Okay. All right. And now if I stop the pulse after the spins are precessed by 90 degrees, it's called a 90-degree pulse. That's one of the key elements that we use to control the spins. A 90-degree pulse will take a spin in an upstate or a downstate and create a uniform superposition of 0 plus or minus 1. Okay. All right, and then you turn off, in the simplest experiments, you turn off the RF at that point in time. Your spins are now in the XY plane, and they're going to continue to precess because they're still in that external field. Now, if you've got a coil hooked up there, you've got a time-dependent magnetic field, and you're going to induce an EMF in that coil, and you pick up a signal, and that essentially decays. That's what we call a free induction decay, and that's the signal we measure. So this is now essentially you know exactly how an NMR experiment works, also an EPR experiment. EPR is electron paramagnetic resonance. The only difference is often EPR is done at higher frequencies because the gyromagnetic ratio of the electrons is much higher. So I'll often have to use a microwave cavity, or I could use a terahertz cavity, or I could even do this with a quasi-optical cavity. None of the physics fundamentally changes as you go forward. Okay, so this is the essence of our experiment. And you could ask, okay, how does this link to magnetometry? So one of the applications that's being used, that is being pushed a lot for quantum sensing, is magnetometry, detecting presence of small magnetic fields. So you know that the Larmor frequency depends on the field. Omega naught is gamma times B naught. And so the more accurately you can detect the frequency, the more accurately you can measure signals around that frequency, right? So what you need is, this, the width of this line. So let's say this is my free induction decay. I can take a Fourier transform of it, and I'll get a resonance peak that has some width to it. Okay, and the precision of my measurement is going to depend on the width of that line. Now, if you've done any Fourier transforms, you know that if you want a narrower and narrower line, you want your signal to last longer and longer. That's why we want really, really long coherence times. Because if we can detect our signal for a long time, I'm going to get very high frequency resolution. Okay, So that's one of the key features of what we want to do in quantum information or in quantum sensing is I want to make sure that my spins have really long coherence times. I want this thing to ring out really long. Okay. Why doesn't it work to start with? So I'm going to give you my first attempt at creating a movie, so we'll see what happens. So most real spins are not in a perfectly uniform magnetic field. The only way you can get a perfectly uniform magnetic field is if you have an infinitely long solenoid. And there are no infinitely long solenoids. The moment you have something that's finite sized and you put it in a real coil, there's a distribution of magnetic fields. And that distribution of magnetic fields is going to have a distribution of Larmor frequencies. So I'm going to look at two cases here where my nominal Larmor frequency is 100. I'm sorry if the scales, if it's not visible. But the main difference you want to see is that this is a narrow distribution of Larmor frequencies. This is a much broader distribution of Larmor frequencies. The range of the x-axis is exactly the same in the two figures. And here what I'm going to do is I'm going to randomly pick frequencies from this Gaussian and see what happens to the signal as I add more and more frequencies. Okay. So they start out with just a single tone. And then as I add more tones, you can see that they destructively interfere with each other, which essentially is what causes the signal to decay. Okay. This is called T2 star decay. It's because in any real system, you'll have multiple frequencies because there's a distribution to the magnetic fields. Even if I take a single spin, if I want to do multiple measurements on it, unless I can make sure everything is perfectly static and nothing changes, I may not have an ensemble in space, but I'll have an ensemble in time that I have to deal with. If I take something that's a little bit broader, you'll see that it decays even more sharply. Right? We sort of understand that from Fourier physics, that something that is going to have a very broad distribution of frequency is going to decay very, very quickly. So if I'm trying to do magnetometry, this is not a good thing because I want to look at small frequency differences, but my background distribution is huge, which makes the static magnetometry really, really hard to do in most physical systems. We often will compromise and do what's called AC magnetometry. We try to detect time-dependent magnetic fields because those are easier to detect than static ones. But in any case, how do I deal with something like this? The way you do it is going back to a really old technique called the spin echo or the Hahn echo. It goes back to the 1950s. And again, this is another animation. This is from Wikipedia from Gavin Morley. And so what you do is you do a 90-degree pulse. The spins will rotate into the XY plane. Then, because they're at slightly different frequencies, they're all going to go at slightly different rates in the transverse plane. But then what you do is you apply a 108-degree pulse, and that flips them all over. And then they keep going at the same rate that they were at, but you get what's called an echo. Let me show you how that works. So that's a 90. This is the spreading. And then the 180 flips it all over, and they keep going at the same rate, but you get an echo. And the spin echo is essentially used in almost every single quantum technology that's out there. Because when you're doing nothing on a quantum computer, you're continuously needing to decouple your qubit of interest from everything else. So you just sit there and apply pi pulses to it so that nothing else changes. So you're always making sure that the system is decoupled from its environment in that case. So this is a Hahn echo. Now you could see that because I've got a signal, it's going to keep decaying, but I could easily put another pi pulse out there, and I could put another pi pulse, and I could put another pi pulse, and then you get what's called a Karp-Purcell-Maboul-Gill train. It's called CPMG for short. And it essentially says you can keep doing this echoing process, and the signal will revive up to a certain point. Ultimately, there's a limit. It's going to interact with everything else, something outside the spin system, and it will decay. But that's what the true limit of the coherence time is. And that's how we actually measure coherence times. So I'm going to pause this one and start this one. And what we do is then we vary this time t. And if we vary t, you can actually see that the height of the echo will decay. And that's really telling you what the true coherence time of the system is. That's something that typically you're unable to refocus. Okay. So when we're trying to do, even if I'm trying to do AC field sensing, I'm limited by this T2 decay. Okay, because that's how long I can record my signal for. And by Fourier relationships, you know that limits the precision with which I can measure some frequency. All right, so my physical system I'm going to talk to you about today, then I'm going to show you some experimental results, is defects in diamond. So defects in diamond are really popular qubit platforms, or I hate to call them qubit platforms because to be a qubit, really you need to be a scalable technology, and diamond's not a scalable technology, but it is a very coherent single spin or a multi-spin system. And so the nice thing about it is that you have very, very long coherence times even at room temperature. And you can put diamond in adjacent to almost any material and study it. So it's a really versatile sensor as well. There are two defects in diamond that we use. One is what's called the P1 center, where you just substitute a nitrogen into the diamond lattice. So you swap out a nitrogen for a carbon, and that's a spin half system. It has very long coherence times, but if you've been paying attention to the hype about quantum recently, you've noticed that there's a lot more hype about what's called the nitrogen vacancy center. The nitrogen vacancy center is a spin 1 defect. In addition to the nitrogen, it has an adjacent carbon removed from the lattice, so it forms a vacancy. And it's just these two coupled defects. In some sense, it becomes one defect. It's a spin 1 defect. It's a 3-level system instead of a 2-level system. But the advantage of the NV center is that it's optically addressable. There's an optical transition, so you can initialize the spins into a well-defined ground state, and you can optically read out the state of the spins. So that's the main advantage of the NV center. The coherence times of the P1 and the NV are almost identical, actually, but they end up. But this one is used a lot, again, because you can actually detect single spins with it. So this is our example. This is an NV center. Whenever you have an NV center, you've got a lot of P1s. The way they create nitrogen vacancy centers is that in some diamond, you introduce nitrogen into the growth process, and so it randomly accumulates to the crystal. And then you irradiate it with electrons to create defects. And when you anneal them, some of those defects combine with the nitrogen vacancies, with the nitrogen, and form the stable NV centers. So you always start with more nitrogen. So there's always more P1 centers than NV centers. You can also do ion implantation. There's other techniques that people are using now to make these nitrogen vacancy centers in diamond. If you look at our experimental system operates at 2.5 gigahertz. So I told you that the frequency omega is equal to gamma times b. This is the line we have here for the spin half system. That's true for the spin half system that we have. And those are the P1 centers. The NV center, because it's a spin 1, actually has a property that has what's called a ground state, a zero field splitting. That is, there's a non-zero splitting between the ground state and a couple of the spin states, even at zero magnetic field. Okay, and that's due to spin-orbit interactions. And so even at zero magnetic field, the splitting between the zero state of the NV and its plus-minus states is about 2.87 gigahertz. It's out here. Now, when you turn on a magnetic field, one of the transitions keeps moving up here, but the second transition moves down, goes through 0, and then comes back up. So we can actually probe the NV transitions at 13 millitesla and 196 millitesla, and the P1 at 91 millitesla. So those are the experiments I'm going to show you. All right, so to do this, we have a home-built spectrometer. So I'm an experimentalist. We have an experimental lab. We go in and build things. So we have this ability to take 2.5 gigahertz microwaves. We phase modulate them. We amplify them. We switch them. We put it into a resonator. This is a loop gap resonator. We also use light to initialize the NV center. So we couple in with a fiber optic. With an optical fiber to shine light on the diamond. And then we have a coupling antenna here that takes the microwave signals back and detects it. For electron spins, your coherence times are short. You typically apply pulses on the orders of a few hundreds of nanoseconds. Your delays on the orders of a few hundred nanoseconds. So you want timing control on some microsecond time scales. And ideally, you want to go as short as you can, so to control these things. So this is a lot of the instrumentation that we put together. This is essentially showing you what the effect of light is on an NV center. So if I run the experiment and essentially do the spectroscopy that I showed you before on an NV center with no light on, that's a signal I get. If I initialize it with a green light laser pulse, it's significantly larger. And so all of the experiments that we do with NV centers, we always prepolarize the spins with light. And we need to do that because there are very, very few of those in the system. We have a lot of P1 centers, and the P1 centers actually can't be initialized by light anyway. All right, so this some pretty pictures to show you what the resonance curves look like. It's a little harder to see, but this is an echo. So you can see the time axis is in the x-axis, and this is the field. So I'm looking at the high field transition for that NV center here, and so the signal in a Hahn echo should peak when I'm right at 0 time, t minus t0, and we can see this is the resonance condition. I also see 2 small side peaks here. These are the hyperfine coupled peaks where the spin is coupling to the other nitrogen manifolds of the system. Yeah. Better. That does better. Thank you. This is the other transition at 13 millitesla. So it's the same NV center, but we just dropped the field now, so we're hitting a different transition. And you can see that the peak is spread out significantly at lower magnetic field. This is the P1 center at 91 millitesla. And again, you can see the central peak and adjacent peaks. And this is due to the P1 center. The electron in the P1 center actually has a 4-fold degeneracy. It can be on any of the axes between the nitrogen and the carbon. And so based on that, you have different resonance lines that show up. And so there are actually, in this case, 5 different resonances due to the presence of that nitrogen, which is a nitrogen-14 nucleus, so it's a spin-1 nucleus. This is a high density of P1 centers. And you can see when you have a high density of P1 centers, all your structure disappears because the spins are coupling to each other, and they essentially, all of the lines broaden out dramatically. And so one of the concerns you'll have is that if I want a lot of signal, I'd love to have a high density sample. The problem is if I have a high density sample, the spins talk to each other. And that destroys my ability to actually do any reasonable sensing. That's a challenge. So this is a high density sample. Again, you do see the signal, but it's definitely blurred out a lot. All right, so we're going to go back and look at rather than doing, those figures I showed you were just one echo, the first echo that we get in a Hahn echo experiment. Now we're going to do the CPMG, where I'm going to keep applying those pi pulses over and over and over and over again. And in some cases, we can apply thousands of pulses. Yep.
I'm sorry to interrupt. Could you go back to that?
Sure.
I
Yeah.
missed what the axes.
Yeah, I'm sorry, I was blurring over them. So this is telling, in addition, the brightness is telling you about the intensity of the signal, and the color is telling you about the phase. So in some cases you'll get a phase that's positive, some cases you get a shift, because you're always, in magnetic resonance, you're always looking at a phase with respect to a reference oscillator, and you're looking at the phase with respect to my reference oscillator that I get. And so this is plotting what the phase that you measure with respect to the reference oscillator in the experiment.
And are these the pre-induction decays?
No, this is a Hahn echo experiment.
So what is the T minus T?
So, okay, so this is actually a great question. Let me orient you. So I do a pi over 2 pulse, a pi pulse, and here we expect the echo at, this is, let's say, tau. This time tau would be where I expect the echo. So the 0 of time on the x-axis is this time here, and we're looking at the growth of the echo before and the decay of the echo afterwards. So if you remember the animation, everything decays out, and then they start to come back. So there's a growth of the echo phase, you hit the peak, and then you continue to dephase. So that's what we're seeing, is that the growth and then the decay along the x-axis. The y-axis is the field, so I'm changing the resonance conditions. Yeah. Any other questions? All right, so here we're going to apply many, many pulses, and you can see this, an echo at tau, 2 tau, 3 tau, and so forth. And what I want to do here is we're looking at 13 millitesla and 190 millitesla, but we're doing 2 different values of tau. So let's look here at 13 millitesla. We have at 13.8 microsecond taus, and that's your decay. But if I change the tau, suddenly my signal decays dramatically. Right? Now, you would think that why should a small change of tau affect the signal going from here to here? At 190 millitesla, I can do the same change, and there's a little bit of a change, but not much between those two. Okay. So this is where we can suddenly see that introduces you to the idea of what's called noise spectroscopy. So these same pulse trains, which are used to decouple a system from its environment, also become uniquely sensitive to certain frequencies in the environment. And so it's a form of spectroscopy of the noise present in the environment, or it's another way of doing what's called noise spectroscopy or AC sensing. So here's, let's take an example of what we're doing here. It's our pi/2 pulse, a bunch of pi's. And here I'm looking at two different sequences with slightly different pulse spacings. Here you can see the echo times are much shorter, and the blue, it's much longer. And now this BZ of t is my random noise, but it has some periodicity to it, okay? And because of that periodicity, what you're doing when you apply a pi pulse, essentially you're doing a form of rectification, because you keep flipping the sign of the spins. You're rectifying the spins. If you look at the ones at the signal in red, you notice that you're actually flipping in an exactly odd integers. And so when you look at the rectified signal, this BZ of t, which had a zero mean signal, has gone into something that's not being a non-zero mean signal at this point in time. And that's because I'm applying it, and I have an odd multiple of periods in there. Whereas the blue, that's not the case. I still have a zero mean signal. So you can see that if I look at the accumulated phase, the one in blue always stays close to zero, but the one in red can diverge quite a bit. And that's that signal that the reason we saw those signals decay very quickly in certain cases. So here I'm going to show you a lot of data. And so this is, again, we're varying tau here. That's a spacing between the pulses. And then this is just looking at the height of the time of the echo, the overall signal. So think about this. This is the total time. This is the time between pulses. And this, you can think about this yellow region is the large signal. The blue is where the signal is decayed away. And you can see that as I change tau, I have an oscillation. And this is a 13 millitesla. I'm operating over here. If I go to the 91 millitesla, I still see an oscillation, but it's much faster for the P1 centers. And this is because at certain spacings, I'm now hitting exactly, there's a periodic signal going in the background that when I'm doing my measurement, and I happen to be applying pulses synchronously with that period of whatever signal is out there, which is how you do sensing. So we're actually detecting a time-dependent field that's present in the physical system here. Now, in this case, I should say, I'm presenting it as a surprise. It's not a surprise. It's something we've known all along. Will be there. And it is the carbon-13 spins. Because you're putting spins in a magnetic field, they have a Larmor precession frequency. And though all the bulk carbon-13s are precessing at a given frequency, that frequency is changing with the applied magnetic field. And now with these experiments, you can actually go in there and reconstruct the spectrum of the carbon-13 noise spectrum. So this is what we would expect at 91 millitesla. It turns out that even when you go to a very high frequency, in this case, this is over 2 megahertz, and we're not satisfying Nyquist conditions for our sampling, but we can actually still detect the presence of these carbon-13s even at high magnetic fields. We just use a slightly modified technique. So now we're really sensitive to these spins in the environment. Okay. Now, we're still studying things only on diamond. The goal for everyone is to say, can I study something outside the diamond? Can I measure variations in the field? And it doesn't matter where that field comes from. So people are using it to study neuronal firing. People are proposing these as dark matter detectors. You can be as long as it has a magnetic field, you can detect it in principle. Okay. You can be, and so but you have really good sensitivity. And what you have to do is, remember, the only way we could detect these is by decoupling everything else. We had to make sure that all the other interactions went to zero. So what we're essentially averaging out here is the interaction between the NVs and the P1s. So the NVs are completely being decoupled from the P1 centers, and that way they're only able to sense the carbon-13. that's present in the lattice.
So this is actually very useful for using the researcher as a quantum computing platform, right?
So it depends. I mean, all platforms have noise, and so there you always have to do with some form of averaging in your system.
You cannot overcome this. You cover them. There's nothing you can do about it.
So if I make carbon-12 diamond, I can get rid of all of those oscillations. So if I have carbon-12 diamond, the hyperfine oscillations do go away. It's the same thing that they did for silicon qubits. If you take donor qubits, if you take silicon-29, natural silicon, the decoherence times are very short. But when they isotypically engineer the silicon substrate to make it silicon-28, which is what the best qubits are now done on silicon-28 substrates, all of the nuclear spin noise has gone away. And so there are places where you can isotypically engineer the materials. And at least for silicon, they do that. For carbon, in some cases, they do that as well. You can actually get growers to make it for you. So again, now I want to come back to this question of what happens when you have spins that interact with each other. So initially, okay, I had the NVs and the P1s interacting, but they're dissimilar spins. When dissimilar spins, the spins interact via a form like SZA, SZB, okay? And what happens now is when I flip the sign of one of the spins from +1 and -1, and I take the average, it's going to go to 0, okay? That's essentially what we're doing in a CPMG or pi pulse sequences. We're flipping one of these between 0 and 1. But if I have spins of the same species, let's say, look at the dipolar coupling here, if I flip both of them, I have 2 -1s, and that doesn't do anything to a dipolar coupling. So applying pi pulses to a strongly dipolar coupled system of identical spins really does nothing to your system. So you cannot average out those couplings. So which is not great if you really want to start to think about getting dense sensors, or if you want to go to a regime where you want to have interacting sensors, maybe you can build entangled sensors, which may be even more sensitive to the field that you have. So of course, at this point, you can say, well, I have an interacting spin system. I know the Hamiltonian of it well. It turns out that by applying pulses to the system, you can engineer the dynamics. And there's a well-defined protocol for doing that. It's called Hamiltonian engineering, or it's based on a technique called average Hamiltonian theory, or also with periodic pulses, periodic sequences, you can apply what's called Floquet theory to engineer different effective Hamiltonians. And that way you can make the system behave in a way that you want it to. So for the dipolar Hamiltonian, it turns out that you can apply radio frequency pulses to either make your interaction Hamiltonian go to 0, which actually is what we do with decoupling. I turn everything off. I could even make it a negative sign because it's a bounded spin system. The Hamiltonian is bounded. So you can actually invert the dynamics and do a time reversal experiment, if you will, and create a Low-Schmidt echo as well in these experiments. And you can engineer and create a variety of different Hamiltonians. But we're going to ignore that. We're not going to go into that area for now. Just if you do that, there's a variety of interesting physics you can study because now you have a lattice of spins that you can engineer the interactions, you can engineer the initial states, and there's a lot of interesting spin physics and condensed matter physics that you can study. You can look at the difference between interacting and non-interacting systems, disorder and uniform systems, and the various types of thermalization physics that might exist in those systems if you're looking at the statistical mechanics of these systems. What I'm going to look at now is, let's go back to this question of dipolar coupled spins and ask, how do we control them? Because really, we talk about how do we tame these interactions. The CPMG was very good for removing interactions between dissimilar spins, but it's not necessarily that good when they're identical spins. So often I'll have a system that will have either local disorder, if it's electron spins, if it's nucleus spins, these are chemical shifts, they're different species, and then you have dipolar interactions. If I'm dealing with nucleus spins, this is a problem that's been extensively studied for nucleus spin systems. So your chemical shifts are typically much smaller than your dipolar couplings. So for example, in an organic solid, this is what my magnetic field, my spectrum will look like. And whereas in a liquid, because of molecular motions, you average out those dipolar couplings and you get nice sharp spectra. So when you try to average out solid state spins, you end up getting things like this. This still doesn't look very sharp. You don't get great peaks. That's one of your challenges. Our goal in a Hamiltonian engineering experiment is to say, I want my effective Hamiltonian to go to 0 or my propagator to go to the identity. This is something that's been done since the late 60s. There's a technique called average Hamiltonian theory, and there's a well-known pulse sequence that people are using or have used called the Wahoo-Ha, named after the authors Waugh, Huber, and Haberlin, just 4 pulses. A 90-degree pulse about x, about minus y, about y minus x. And what's interesting about that is, like, if you take a solid system like adamantane and look at its decay, this is its decay if you do nothing. It's reinduction decay. It decays in less than 100 microseconds. If you apply the Wahoo-Ha sequence, you can go up an order of magnitude to getting a little close to a millisecond. If you do this other sequence, which is a more complex sequence and probably the best known sequence in terms of decoupling dipolar interactions, it's a 48 pulse sequence called Corey 48. It goes even further, but it's still not near the T1. We call the T1 limit. That's a time scale in which the system interacts with this environment. So here, rather than applying pi pulses, we're applying pi over 2 pulses. That's the tool that we use to control the system. We're not applying, because you can't, remember the pi pulses do nothing to the dipole coupled spin system, whereas a pi over 2 pulse does. There's a variety of effects that show up. The reason some of these pulses work better than others is because they're sensitive to errors in different ways. If you don't calibrate, you can under-rotate or over-rotate. When you apply a pulse, you think you're applying this, but most of the time you're actually applying this, where your pulses have some shape to it, and you think you're applying a pulse along x, but there's also a component along y because your system has a complex response function. And so there's all sorts of non-idealities in your system that show up. Plus, it might be hard to be on resonance to all the spins. This, by the way, is what a 48 pulse sequence looks like. It was designed analytically. So it was a tour de force, and no one's done it. No one's tried to do experiment calculations like that because they're hard. So what do people do? Well, just take a step back and look at some more data. So I told you the CPMG works well for NV centers. So you can see that the NV center, I can get about 100 microsecond decay times with the CPMG. If I use the Wahoo-Ha, it's maybe a little bit better. So actually, there were probably still some dipolar couplings present in my system. If I look at the P1 centers, the CPMG doesn't do very well. It's on the order of a few microseconds, 2 to 3 microseconds. But I can go up to 30 to 40 microseconds over here when I'm using the Wahoo-Ha sequence, because when I really take into account and remove those dipolar interactions actively. What's happening at these short flip angles is something that we're still figuring out. When you go to a very small flip angle, your signal disappears, but it looks like there's a long tail, and we don't know if it's real or not yet. So we'll come back to that another talk, another day. So how do we engineer these things? So I told you the way we did things like Wahoo-Ha and Corey 48 were done analytically. They're computationally exhaustive, and you're essentially calculating commutators between every pair of time periods in your system. And so the longer the sequence you get, it becomes really, really, really tedious. There are recently, from Misha Lukin's group at Harvard, they've been using these same techniques to look at dipolar coupled electron spins, both for their sensing experiments as well as their experiments on time crystals and studies of many-body localization and so forth. And they've come up with some really nice sequences. And the reason things like Corey 48 don't work as well for them is because in electron spin system, disorder is dominant. Disorder ends up being much stronger than the interactions that are typically used. And so you need a slightly different set of you're operating in a slightly different regime. So they've come up with a couple of sequences called Droid 60 and Dirac 2, but they use the same general idea. They use average Hamiltonian theory, but they've combined it, they've synthesized it into a set of rules, 5 or 6 rules, and then they do a numerical search for sequences and say, do they satisfy the rules? Do they not satisfy the rules? If they satisfy the rules, we're going to consider them, and then they find the best performing of these sequences. We've also, simultaneously, we've been looking at seeing if whether machine learning or reinforcement learning specifically could be used to engineer new sequences. Because again, I want things that work well, but the cost of actually calculating them is high. Hence, yeah.
This 24 medium line sequence, would that be very repetitive to YXX?
It's a 24 pulse sequence. This is a 48 pulse sequence. This is a 24 pulse sequence. It's not a consistent naming structure. Every group gets to choose how they name their sequences. So these were two reinforcement learning sequences. The way these two were built is that we used reinforcement learning, but then we had to add physics in at the end, because reinforcement learning on its own was unable to come up with the best sequences, and we don't know why. And since then, we've been working on it, and I think we've gotten much better because we were novices on using machine learning, and machine learning tools are also growing faster than probably anything else that is growing. So AI is a very dynamic field. So we're probably always 2 or 3 years behind where AI is in some ways. So what we've been doing is using reinforcement learning. I'm not an expert on it. Our target, the key thing that you need to think about here is our target is identity. I want to apply pulses to make the system stop evolving. I don't want it to interact with anything else. And my reward, essentially, is do I win or not, is what's my fidelity? How close can I get to a fidelity of 1? Okay. And so the way we do that is we look at the fidelity between my target, which is identity, and the actual unit area of the sequence of the sequences of pulses I apply, and we take the log of 1 minus that, because it really blows up as you get close to 1, and so you can really get fine measures. And then we, of course, apply neural networks. We come up with we use right now. We started with alpha 0. We've gone to mu 0. There's some variations in the reinforcement learning tools that we apply. And then the main thing as physicists, what we're trying to do is say, let's put the physical intuition into our action space. What are the actions an actor can use when I'm trying to compose these pulses? When we started out, we were saying, well, the simplest pulses are the original space is like, well, every sequence that's been composed so far has built out of 90-degree pulses, x minus x, y minus y. That's it, and delays. So let's start with that. Turns out that doesn't do really well. But then we also realized that then in the previous paper, we saw that this YXX, Y pulse and X pulse and X pulse, did seem to do quite well, and we came up with some good sequences. More recently, we've studied these what are called spin echo plus delay sequences and spin echoes, where it's an XY delay. And those are really nice because at a base level, they decouple dipolar couplings to 0, even at the elementary unit. So every action essentially decouples it to 0. And so when you do that, you can then tune various parameters, whether your system is exploring or exploiting given opportunities. It's kind of like an annealing algorithm. And you can also optimize for the errors in your system and the degrees of disorder and interaction present in the system. And we have a variety of, we've essentially done all of our simulations right now for the NMR types of platforms where the decouplings are strong compared to the inhomogeneities. And we found these two new types of sequences, SED36 and 36 error, are purely reinforcement learning based. We've done no manual manipulation except by putting the physics in right at the beginning. They're saying this is what the rules of physics will tell us. Okay, and so there's a variety of ways in which one can build these sequences. I told you about Droid 60 is numerical, but still average Hamiltonian based. YXX 24 and 48 was reinforcement learning plus a manual. And then a previous iteration of us was SED48 again. The names don't mean that much. Gold standard, Corey 48 was the analytical, and Dirac-2 seems to perform really well. So we've compared some of our sequences to Dirac-2. The X regime is where NMR typically operates, and the Y regime is where like EPR typically operates. And so if you're up here in this color range, then Dirac-2 is performing better. If you're down here in this color range, then the sequence that we're looking at, Corey 48, YXX, SED, or whatever, is performing better. So we see that if you're up in this region, Dirac-2 does perform really well for those. In this region, YXX does too quite well, but many of these sequences are pretty robust across all ranges. And in fact, especially out here, something like SED36 error does a dramatic improvement over something like Dirac-2 in the NMR regime. Of course, Direct2 was not designed for the NMR regime. We're just trying to, at this point, we're trying to look at, can reinforcement learning provide additional insight and tools into how we calculate or design these decoupling and decoupling sequences. We can look at sensitivity to errors. There's really not that much sensitivity to error, but on average, you can see some of these sequences are, these new SED sequences that we've come up with seem to work really well. I should say that the proof of all of this is only going to come up when we follow it up with experimental results, which is happening now. But that's when we really know it works. Because a lot of things work really well on paper, but you don't know how well it works until you actually try it in the lab. So these are, if your RF is not applied on resonance, that's an offset error. Phase transients, these are these pulses in the wrong axis that are applied occasionally. And again, they're not that sensitive, but they do have an effect. And finally, rotation errors are more complex because you can coherently drive your system into the completely wrong regime if your errors are large enough. So there's just a variety of different ways in which one can think about decoupling spin systems. The key message I want you to take is that reinforcement learning can actually design sequences that are as good, if not better, than the sequences we're doing manually. And you can also be tuned to specific error models and specific regimes that your system might have. So it's not a one-size-fits-all, which has previously been the case, like, okay, everyone just used one sequence, independent of what you were actually trying to study. Now you can look at the system you want to study and design a sequence for that system. All right, so decoupling allows us to simultaneously suppress unwanted interactions I showed you, but also become uniquely sensitive to certain signatures, like the AC sensing and the noise spectroscopy. And then reinforcement learning is a really interesting tool with which to start thinking about designing new sequences. And we looked at the simplest control problem, which is turn everything off. That doesn't mean that's all you can do. You can always ask a more complex question. You just have to guide the algorithm in the appropriate way to get it to where you want to be. All right. I'm going to end with another set of acknowledgements. Those are the people who did all the work, and thank you for your attention. I'm happy to take questions.
Thank you. Yeah.
So we have one up there, here, all over.
Oh, sorry. I'll go to Sean first. I'll come back to Dima and then up.
So I guess I don't get what is the question for the NV center exactly. So so we know it forms a qubit. Okay. And then you can see the nice echoes.
Okay. So
and then at which point is what's the critical step to do quantum computation?
So this, I don't think the NV center is going to be a good quantum computer. I think it's a fabulous quantum sensor. So it's right now already being, you can put it on a tip and use it.
You mean as a magnetic field sensor?
Magnetic field scanning or temperature scanning. It's also
better than SQUID?
Sorry?
Better than SQUID? SQUID.
Sweet, yeah. Yeah.
In terms of sensitivity. So what's the field sensing?
It's not as good, but it's nanoscale. So you get the spatial scale is tens of nanometers compared to the SQUID, which is microns. So the best sensors in terms of sensitivity are always going to be atomic gases. Atomic gases have longest coherence times except for their bulk, their centimeter scales. I mean, people are trying to shrink those down as well. But the problem is when you shrink them down, their coherence time also drops with atomic vapors. So there's always this trade-off of, okay, the best, if I want the most sensitive ones, you use a surf magnetometer in the atomic gases. But your spatial resolution is horrible. The NVs give you very good spatial resolution. They sort of live in this middle space where you can get tens of nanometer resolution, and potentially scan it on the surface on other materials. Because a diamond is a relatively inert material, you can put it up against almost anything else. Now that doesn't mean it's the only one. There are other. All you need really is defects in wide bandgap materials are all really promising. So people are looking at silicon carbide, defects in HBN. All of these have defects in silicon carbide. They all have.
Can you put on like a submarine to detect like the And underwater target?
So people are trying to do, there are medical applications. You can flow water over the sensors and couple into to study proteins in the water as well. So there's a variety of applications like that.
So I have a question about something that was rather surprising to me. You mentioned that there was no progress with analytical tools to improve multiple sequences since Core 48 sequence, that is 1990. And so it's surprising to me because the prescription how you in principle improve those sequences has been known for decades. And of course it's extremely hard to compute, but you don't have to do it by hand. You could use computer-assisted derivation. So why wasn't there progress?
So the main reason is because, again, all of this was done in the NMR community. And in the NMR community, the way people narrow lines is by magic angle spinning. And magic angle spinning is much more robust to be put in. These sequences, as you see, that if I don't tune the sequence right, if my pi over 2 pulse is off by a little bit, or if I have an error, there's a huge difference in how it performs. So user to user, there's a lot of variation in these sequences. Whereas magic angle spinning, you turn it on and it works, and it's much more robust. From a practical application, and magic angle spinning just won, and people stopped working in this area. So there's almost like been a revival of interest in this area from quantum information, and again, primarily from within people working in spin systems, again, NVs and diamonds. Yeah.
Okay, thank you.
I think there's a question up there. Or one here and one up there.
Can reinforcement learning be used to determine or perform an adaptive search with different possible dynamical decoupling sequences in the context of quantum circuits? So like if I were to give you an arbitrary quantum circuit, would it be possible to determine the best possible dynamical decoupling sequence that can adapt to the quantum circuit to suppress noise? And the qubits to which I must apply those DD sequences?
It depends on what your noise model is, right? Because independent of a noise model, or if you give me a full characterization of all the possible error sources, in principle, yes. But without a model, the more interesting question in a case like that is, could you use feedback to actually tune your decoupling sequence? And that would be more, so this is all open loop control. If you did closed loop control where you applied different dynamical sequences, decoupling sequences, and then learned from those and did a feedback, because the cost of understanding your errors is often much higher in practical platforms like that than the cost of designing a sequence.
Right.
Yeah.
Thank you.
I actually had a similar question. So when you inevitably do the reinforcement learning on your real system, do you think you can like extract out the interesting physics from the like idealized pulse sequence?
So we'd love to. The challenge is if you want to, the places where people have really done feedback control is when you're able to do a weak measurement on the system, on the dynamics as it's occurring. So you need to have a very good measurement protocol. In all of the work we've done so far, we are doing weak measurement, but it's only on an ensemble. And if you do strong measurement, it doesn't hurt. You're essentially open loop feedback. I mean, closed loop feedback is not very effective. So it's, I think a little bit depend on whether your noise model is time independent or time dependent. If you're doing a time dependent noise and you want to you think about continuously steering your quantum state, then it becomes much harder, because what you want to do then is introduce an ancillary at certain times to probe where the system is, measure the ancillary, and then change your control. And I think that's possible, but I don't know if magnetic resonance is the platform on which that'll work really well. I'm still not sure about that. I think it's a possible way to do in which one can do control and do steering. Yeah.
Any other questions? None? Then thank you, Shekhar.
Thank you.
Thank you.
I need to call SAS. 1, 2, 3. 1, 2, 3.
If I put a backing track on, will you start singing?
No?
What song do you want?
I want My Way. I always want you to do that. I tried it once.
What song do you want?
My Way.
Karaoke.
Karaoke.
Frank Sinatra, My Way?
Yeah.
Okay.
With a light. That's. And now the end is near, and so I face the final curtain. My friend, I'll say it clear, I'll face my gaze. I want the lyrics. And now the end is near, and so I face the final curtain. My friend, I'll say it clear, I'll state my case with some certain. I've lived a life that's full. I traveled each and every highway and more, much more than this. I did it my way. Regrets, I've had a few, but then again, too few to mention. I did what I had to do and saw it through without exemption. I plan each starter course, each careful step along the byway. And more, much more than this, I did it my way. Yes, there were times I'm sure you knew when I bit off. No. But through it all, when there was doubt, I did up and spit it out. I faced it all, and I stood tall, and did it my way. I've loved, I've laughed and cried, I've had my fill, my share of losing. And now, as tears subside, I find it all so amusing. You think I did all that, and may I say, not in a shy way. Oh no, not me. I did it my way. For I is a man. What has he got? Even know himself. Then he has not to say the things he truly feels, and not the words. Who knows? The record shows I took the blows and did it my way. Yes. It was my way.
Elena. Why have all the lights turned off? That was so dramatic.
It's done.
No way.
Make it dramatic.
Okay, choose the song.
You choose the song.
I don't know. I don't know what song I want.
No? That way.
If I do Bohemian Rhapsody, will you do it with me?
Yeah.
Yeah, let's go. No, I have a better one. I want it that way.
I want it that way.
Yeah.
No, you can't. No, you can't. You can't. I'm sure you can.
Yes, I can. I can. I can. I'm scared. Wait. You are my fire, the one I'll unlock it. Desire, believe when I say I want it that way. I don't know the lyrics, but no wait, I don't know this part. Oh, I missed it. Wait, that way. Tell me why ain't nothing but a heartache. Tell me why ain't nothing but a mistake. Tell me why I never wanna hear you say I want it that way. Bro, no, that was horrible. Desire, yes or no. It's too late, but I want it that way. Tell me why ain't nothing but a heartache. Tell me why ain't nothing but a mistake. Tell me why I never wanna hear you say I want it that way. Bro, no. That is the extent.
Unexpected.